Hi everyone, I am Jin. Today we are going to talk about an SoK on the topic of TE-assisted confidential smart contract. In this work, we will explore plenty of existing related literature and in production projects. Specifically, our work includes the following contents. We first introduce the concept of TE-assisted confidential smart contracts. We then propose our evaluation framework to give a high-level view of this work. We evaluate both the desirable properties for the smart contract services and the potential issues for the blockchain system. Lastly, we point out the research challenges and give some research insights. A smart contract is a computer program stored on a blockchain and run in a distributed network. The contract has two major properties of automatic execution and non-equivocation. Automatic execution means a smart contract can force one entity to execute operations based on predefined logic. Non-equivocation means each distributed node can hold a global view of the state at a specific height, supporting more efficient settlement. However, using smart contracts still confront many challenges. The most identifiable drawback is the lack of confidentiality. The operation code and the contract state are completely transparent, and any state and its changes are publicly accessible and observable. For instance, smart contracts in Ethereum cannot be directly applied to the following two applications, which is the victory auction and the voting application. The bid and vote required to be hidden from the public, but this cannot be realized for a transparent on-chain smart contract. Different from the conventional smart contract, a confidential smart contract aims to hide the contract state so that the public cannot see any useful knowledge of the states. Currently, many technical privacy-preserving solutions have been proposed, such as the techniques of zero-knowledge proof, multi-party computation, and homomorphic encryption. However, this solution requires an increasing of computation complexity, making executions run slowly. In this work, we focus on the trusted execution environment technique, which is short for the TEE. TEE can protect the data in use by performing computation in a hardware-based environment. There are four major features in TEE, namely the confidential execution, sealing technology, local attestation, and remote attestation. We introduced the notion of TEE-assisted confidential smart contracts. It combines the hardware-based TEE to existing blockchain architecture, especially in its storage layer. The participants will equip the TEE into their operating nodes, ensuring every input, output, and execution can be physically sealed. Although various TCSC protocols have been proposed, newly released projects may fail to draw upon the experience learned from existing protocols, such as repeating known design mistakes or applying cryptography in unsecure ways. We, in this paper, aim to abstract a high-level framework to simply and clearly systemize the knowledge on current TCSC schemes. We attempt to capture some comments among this project regarding their features, properties, and the potential security vulnerabilities. Here we introduced our unified evaluation framework. We consider two parts, the smart contract use as services and the underlying supporting blockchain systems. Based on their operating mechanisms and the ways of combination, we investigate and categorize a set of typical protocols into two main classifications, the Layer 1 solutions and the Layer 2 solutions. The framework covers corresponding two aspects. desirable properties for contract services, and the security consideration for underlying systems. Specifically, we discuss the desirable properties from typical properties that inherit from the traditional smart contracts and featured privacy-related properties. Meanwhile, we emphasize practical issues, pitfalls, and remedies in designing TE-assisted blockchains. Before diving into specific evaluations, we provide a lightning tour of how a typical confidential smart contract operates. Totally, 4 steps are included: loading the inputs into the contract engine, computation inside the TEE, conducting consensus, and returns the outputs. We classify current solutions into layer 1 and layer 2 by investigating whether the step 2 or step 3 are executed within the same TE. For layer 1 solutions, all the operations are operated within the same TE, whereas for the layer 2 solutions, step 2 and step 3 are separate but still within the same node. Here we present our identified details in terms of desirable properties. We evaluate each TCSC system from 2 aspects, mainly from its privacy-preserving property and the blockchain intrinsic feature. The privacy-preserving properties include specification, hidden input-output privacy, procedure privacy, and address unlinkability and anonymity. The blockchain intrinsic feature contains the immutability, consistency, interoperability, availability, decentralization, automation, variability, and some specific mechanisms. As for the security consideration, we give our discussions from the following aspects in terms of all TE components. TE hosts the security for punishment and incentive mechanisms and fault tolerance and authentication. This mainly targets on the host level. TE security for each subcomponent on attestation, memory, timer, and related physical attacks. This mainly targets on TE hardware. TE program security for workload measurement, flaw detection, query restriction, and chain data confirmation and output conflicts. This mainly targets on the code level. TE key security for distributed keys, key rotation protocols, independent contract key, and independent TE keys. This mainly targets on the key level. Based on our evaluation framework, we provide detailed evaluation results towards 17 in the world projects. We analyze each of them with our evaluation metrics and summarize the output with 2 large tables. Here we give a very concise version to compare the features of both layer 1 solution and layer 2 solution. Layer 1 solutions are mainly built on the top of consortium blockchains, while the layer 2 solutions are based on the public blockchains. The layer 1 solutions are good at its system availability, and the layer 2 solutions for performance well at the scalability. Lastly, we point out the research challenges of TCSC protocols. We give 3 types of disadvantages existing in the current systems. The side channel attack is inevitable because all types of TE suffer from such attacks. This cannot be avoided by the software. The key management dilemma refers to 2 aspects. Firstly, putting the application keys in a single TE will contribute to the key security, but also increase the risk of single point failure attack. Secondly, sharing the private key among multiple TEs offer practical availability, but increases the key exfiltration risk. The third issue is the transparency barriers. The precise architectures of chips are still unclear for some TE products. Meanwhile, the attestation service used to prove that a program runs inside TE is non transparent. Finally, we summarize this work as follows. We provide a systemization of existing TCSA systems driven from academic work and in production projects. We establish a unified evaluation framework for confidential smart contract systems. We consider two parts, the smart contract used as services and the underlying supported blockchain systems. We conduct a comparative analysis of existing protocols based on our evaluation framework. We discuss the systems both from their common designs and the distinguishing features. We further give a comprehensive discussion of current designs and implementations, comparisons between the layer 1 and the layer 2 systems from the perspective of security, efficiency, and easy adoption, and the common issues on public availability. We also point out the research challenges in this field. Here are the references used in this work. We thank for your listening.